Have you ever stopped to think about what's actually going on inside your phone or your laptop? We're about to pull back the curtain on the one single brilliant design that powers pretty much every digital device you've ever used. Let's get into it.
I mean, seriously, think about it. You click on a link, you tap an app, and poof, something just happens. But what is that something? Well, in that silent, invisible world inside the chip, this elegant, almost 80-year-old process just kicks into high gear, and we're going to see exactly how it works. So here's our game plan. First, we'll look at the universal blueprint itself. Then, we'll meet the two key players, the brain and the memory. After that, we'll check out the three-step pulse that brings it all to life, we'll follow a single command on its journey, and finally, we'll ask why this blueprint has stuck around for so long.
All right, let's start with the big idea. It's called the von Neumann architecture, and you can think of it as the foundational DNA for almost all modern computers.
So what's the big deal here? Well, it all comes down to one word: simplicity. Imagine you're baking a cake. Before this idea came along, it was like the recipe, the instructions, was kept in one kitchen, and all the ingredients, the data, were stored in a totally different building. The von Neumann architecture said, hey, why don't we put the recipe and the ingredients in the same pantry? It sounds so obvious to us now, but at the time, this was a total game changer.
And that simple idea leads to a couple of core principles. First, just like we see here, you've got one shared memory for everything, instructions and data, living together. And second, the computer's brain, the CPU, works through its to-do list one step at a time, sequentially. It grabs an instruction, figures it out, and then does it. Simple, powerful, and it just never stops.
Okay, to really get how this all works, we need to properly introduce the two main characters in this story.
So on one hand, you've got the CPU. That's the brain. It's the active part, the worker, the one doing all the heavy lifting and the thinking. And then you have the memory. You can think of it like a massive library. It's totally passive. It just sits there holding all the books. And both our recipes, the program instructions, and our ingredients, the data, are all just sitting there on the shelves waiting for the brain to ask for them. So how do these two, the brain and the library, actually work together? It's all thanks to a process that is, and this is no exaggeration, the actual heartbeat of the computer. It's this constant, repeating, three-step pulse that's happening billions of times every single second.
And here it is. This is the secret sauce. Everything, and I mean everything a computer does, from loading a web page to playing a game, boils down to this incredibly simple three-step loop: fetch, decode, and execute. That's the whole cycle. Let's break it down.
First up, fetch. The CPU's control unit, acting like a head librarian, goes over to the memory to grab the very next instruction on its list. And it knows exactly where to look because it has a little bookmark called the program counter that's always pointing to the right page.
Okay, next is decode. The instruction that was just fetched is written in machine code, which is basically gibberish to the part of the CPU that does the actual math. So this step is all about translation. The control unit translates that instruction into a clear set of commands that the arithmetic logic unit, or ALU, can actually understand.
And finally, we get to the fun part: execute. This is where the action happens. The ALU gets the translated command and just does it. Maybe it adds two numbers, maybe it compares some data. Once it's done, the result gets stored, either in a super fast, temporary little cubby right there on the CPU called a register, or it gets sent all the way back to the main memory library.
All right, so that was the theory. A little abstract? Maybe? Let's make it real. We are going to follow one single, simple machine instruction as it takes a trip through this entire cycle. Okay, our example instruction is add R1, R2. Now that looks a bit technical, but in plain English, all it's really saying is, hey computer, take the number you've stored in that fast little spot called register 1, add it to the number in register 2, and then overwrite whatever was in register 2 with the new total. That's it.
So let's watch it go. During the fetch phase, the CPU just goes and grabs this add R1, R2 command from memory. Then, in the decode phase, the control unit looks at it and goes, aha, I see what's going on. The operation is add, and the ingredients are in R1 and R2. And finally, in the execute phase, the ALU steps up to the plate and actually does the addition. Fetch, decode, execute. Done.
We can even get a little nerdier and zoom in on just that fetch phase. First, the program counter, our bookmark, holds the address of our add instruction. That address gets copied to something called the Memory Address Register, or MAR. Think of the MAR as the call number you give a librarian. Then, the actual instruction is pulled from memory and put in the Memory Data Register, or MDR, ready to be decoded. And, this is the crucial part, as soon as that happens, the program counter immediately flips to the next page, getting the bookmark ready for the very next instruction in line.
So we've seen the architecture, we've seen the parts, we've seen the cycle. Now let's ask the big question. Why is this really old idea still so incredibly important today?
You know, in the world of technology, things are obsolete in a year, maybe two. But this design, it's been the bedrock of computing for nearly 80 years. That is just an incredible testament to its power and its elegance. It's like the Model T or the light bulb of the digital age.
So here's the main takeaway, the one thing to remember. Every time you play a game, stream a movie, send an email, anything, it's all just this incredibly simple three-step dance. Fetch, decode, execute, happening over and over and over again at mind-boggling speeds. Every complex thing you do is built from these tiny, simple steps. And that just leaves us with a pretty cool question to chew on. This sequential, one-step-at-a-time design has powered the entire first digital century. But as the things we want to do get more and more complex, what's going to be the next revolutionary idea that powers the century to come?